to determine the work done by the individual forces, let's say it's being lowered, which means that positive work is being done by gravity. And even if I simplify it out and say that the net force is 0, so that the object's not accelerating, an unnecessary condition, by the way. We could have the system accelerate. But let's just, for the time being, say it's net force of 0 and the box is lowered at a constant velocity. Then the work done by gravity is actually pretty easy. That's going to be 1,500 times 20. We know the force downwards is the weight of the box. That's 1,500 newtons. And the box is lowered 20 meters. So in the short run, the work done by gravity is not bad. Not a difficult calculation. Can I assume that that's not too difficult a concept? All right, so we got 300,000 joules of work. Yesterday, the example gave us forces that we could easily kind of throw out that weren't doing work in the system. But in the case of this example, both of these cables are doing a different amount of work. It's not equally shared. And moreover, unfortunately, you would have to do net force first. Yes, ma'am?
Why isn't it 30,000?
I'm sorry, because I'm in a hurry, I guess. And I didn't have the benefit of my calculator in front of me. But thank you. That's okay. Jackson can't see it at all because I'm using the red ink again. Sorry, man. That's okay. I think Jackson doesn't feel very good. Do you not feel good? All right. So to actually solve this problem, the only way you're going to be able to figure out the work done by the individual forces of tension is to know what the tension forces are. There's just no other way around it. So this problem is definitely more complicated than yesterday's. You would have to do the net force problem first, identify the two tensions, T1 and T2. But then once you've identified the two tensions, the calculation of work actually becomes very simple. I mean, the work done by T1 is merely going to be T1, and then you do need the angle. You could use this one or this angle. It won't make a difference. So it's going to be, 110 degrees probably. Work that out, you'll get the negative work done. And then the work by T2 will be similar. This one will be 130 degrees. But again, you can't figure that out until you know T2 and T1. The calculation of the work isn't the hard part typically. It's understanding what's doing work. The net work in the system will equal 0. It will have to, because we know that the net force equals 0. So if you want a bit of a challenge, a bit of practice tonight, this isn't a bad practice. It's a good start. These are not the kind of problems that I really want to spend a lot of time doing. But I did put together a mastering homework assignment. It's posted. I didn't give a lot of turnaround for it. Next Tuesday at midnight. So that gives you, 5 days. I know it's not a full week, but let's face it. I've been kind of falling down a job when it comes to giving you guys assignments at home. So I'll make sure I make up for that next couple weeks. Look, it's not punishment. So I don't want to work this any more than that. But if there's a question out there, I'll handle it. Okay. There are 2 other review items from last year that I would be remiss if we didn't talk about. So let's talk about the first one. Last year, we assigned this idea that there was potential energy in springs We would call it elastic potential energy. And anybody who had physics last year should know that the elastic potential energy is related to the strength of the spring and how much the spring is compressed. I hope that you've noticed I have not used the word potential energy yet. There's a good reason for that. So I'm going to continue to not talk about potential energy for a little while. I'm using this to activate your prior knowledge from last year. So we're going to begin to develop a more complicated relationship between variables here. We've been pretty straightforward in this concept of work so far, in that we've had easy to identify forces acting on objects. However, the moment we start talking about interactions, the problem becomes more difficult for us to stratify. Let me kind of put together a quick picture of what I mean. So consider a standard spring with some kind of background there that allows the spring to be stretched in a uniform way. And that the spring has spring constant K and is firmly affixed to the wall on one side, so that the spring can't easily move someplace. Now, this part's tough, so I want to try and be very careful with the words I use. If the spring were to be compressed, that's the word choice I want to use. If the spring were to be compressed a distance x, the spring would apply a force to the left from a displacement to the right. This is the force from the spring due to its compression. Now, I'm not talking about how the spring came to be compressed, merely indicating that if the spring were compressed a distance x, the spring would push to the left in order to move the spring back to its relaxed position. Everybody understand the way in which I'm saying this? I'm not talking about how the spring got compressed. I'm merely saying if the spring were compressed to the right, then there would be a produced force within the spring to try and restore it back to the left. Everybody good so far? All right. Because when we calculate work done on a spring, it's different than work done by a spring. I want you to think about this and get this in your notes and delineate between the two so you can't say I didn't tell you, and have something that you're using to study. I'm going to hit pause. The spring can do work on an object, and an object can do work on a spring. When we talk about these details, we're trying to track the flow of energy. The spring represents the first force that we're dealing with that is an actual interaction, meaning work is only done when the object interacts with the spring. This is different than other forces we've talked about. The other forces were kind of applied to the object by some invisible hand. The guy standing at the top of the ramp, he was never a part of the problem. The force applied to the block to get it up the ramp, we don't know what applied that force. In this instance, we can't talk about the force from the spring without also talking about the spring. That's what I mean by an interaction. The reason why I haven't brought up potential energies is because potential energies all arise from the interaction of two or more objects. Potential energies all arise from the interaction between two or more objects, which makes tracking the energy sometimes difficult. Let me throw out a hypothetical using something you know about from last year. If I lift a book, you would probably tell me that the book now has energy. What kind of energy does it have? Raise your hand if you know what gravitational potential energy is. Like you could calculate it. It's not very many of you to remember that it's mgh. And if you recall from last year, that calculation required that we had an established 0 point for reference, correct? Like the ground could be 0. Now, you guys who didn't have me last year, you don't know this, but I spend a lot of time referencing this concept that potential energy is relative, that we establish what we call 0. So lifting something above the table suggests that the table is 0. But if I shift that object from where it is to over the floor instead of the table, did something suddenly change about the object? I mean, if you're not understanding, imagine this. Springs, the interaction is between the object and the spring, but it's not just the spring. If this wasn't here, how do you compress the spring? Right, if I bring a box, and I'm going to say I'm going to put a box on the table that I'm going to use to store some energy by pressing it up against the spring, and I go ahead and take that box and push it this way, am I going to store any energy in the spring now? No, I can't. If I push the box to the side, the spring just moves to the side. So when it comes to all forms of potential energy, they are going to be an interaction. Some kind of way in which two or more objects interact. The spring stores energy because there's some other thing there that roots the spring in place, that allows for the spring's length to be changed under the action of another object. So, if the box compresses the spring a distance x to the right, does the box have more energy? And I am intentionally being difficult here. And I'm not trying to trick you. I'm trying to make you understand that when we talk about doing work in these more complex environments, we need to be very careful about where these forces are and in what direction they act. The box necessarily has more energy than before, but not because the box is different. It's because the box is now a part of a system that has more energy. The box spring wall system now has more energy. The potential energy is stored with all of them. I mean, if the wall was particularly weak, the wall could suddenly spring to the right under the duress of this box, and the box could stay in place. The system stores the energy. Okay so far? So, what I'd like to do, and I'm not trying to make this overly complex, but in a moment, we have to deal with gravity in a whole new way. And I want to just be very clear, we need to be careful about what we say when we talk about work being done. Let's calculate the work done in compressing the spring. Okay? The work done in compressing the spring will begin with us looking at an integral. I put delta there, but I should be putting a d there, sorry. Now, right now, I want to talk about the work done by the spring on the box. Does everybody understand? I'm being very careful about my word choice here. The work done by the spring on the box. So I'm going to take the system, which looks like this, where right now the spring is in its relaxed state. And I'm going to change the system. Give me just a second. So that the box now has moved the spring a distance x. So I'm going between state 1 and state 2. Is everybody okay with that? What direction does the spring push on the box? So can I get everybody's agreement on that? That the spring, the force from the spring is to the left. Everybody good? So the displacement of the box was to the right. Everybody good on that too? Okay. We're going to construct an integral that takes the box from 0 to a distance x. Let's say x final so that I don't get too confused with what x is. There is a force from the spring that's to the left. Basically what I'm doing is I am trying to account for this negative sign in setting up my integral. So I know that dx is going to be to the right, but the force from the spring is going to be to the left. So I am going to make sure that we all know that my dot product results in me requiring a cosine of 180 degrees. This is accounting for the negative sign. The size of the force isn't so bad. I can drop it in now since I've accounted for the direction by just dropping in kx cosine 180 dx. Now your book doesn't do it this way. Your book doesn't talk about the direction at all. Your book just blindly drops in negative kx in for f without indicating that we're looking at what the spring did while being compressed. I am trying to clearly focus you that what we are calculating here is the work done by the spring. This is not the work done on the spring. This is the work done by the spring. Okay? So, let's go one step further. I'm going to go to another page if that's okay. I have a table. Table leg. And floor. Okay? So, there is on the table a box. There's always some stupid box. Now, I take the box and I lift it a distance h above the table. It has gravitational potential energy now, right? Because it's above the table. Does it have more energy now? Now, I mean, look, was any work done on the box to move it from here to here? Careful. I don't know. I definitely know that it probably wasn't the amount of potential energy it just suddenly gained. Because whatever horizontal force pushed the box sideways, it probably wasn't very much. And it didn't move it very far, but suddenly its amount of potential energy, what, tripled? It's got 3 times the distance to fall now as it had before. Did it really look like I did 3 times the amount of work just sliding it a couple of centimeters to the side? Now, I'm bringing this up to you because the energy is not in the book or the box. The energy exists between the object and the center of the earth. It is the interaction of this object with the earth that creates this potential energy. The book doesn't have it alone. The book earth system now has more energy than it had before. So when I say that we have to be a little more careful about our framing of potential energy, it is because all potential energy systems are in interaction between more than one object. I guess not that page. This page. Now, from this point forward, I'm not going to have so much gravitas in my voice because all we have here is a pretty straightforward integral. There's a -1 and a k that are both constants. So they are not a part of this integration. So I can take them outside the integral. What I have left with is one of the easier polynomial integrations, right? You guys have done the antiderivative of x with respect to x. So I don't think I have to work that hard to tell you that this is going to be 1/2 x squared evaluated from 0 to x final. Now this is the part that's weird, okay? When you finish this, you will get -1/2 k x final squared. This means the work done by the spring was negative. I know that seems weird, but the work done by the spring on the box was negative. Now tomorrow we're going to come up with why that's negative. But I want you to imagine this for just a minute. If the box had been slid towards the spring with some velocity, it would have kinetic energy, right? Didn't the spring, by necessity then, have to take the energy away from the box? So this has to be negative so that we have consistency. When the block makes it to the bottom of this hill, even if we've not studied conservation of energy, you understand that there would be an unbalanced force that would act on the block that would accelerate the block so that when it made it down here, the block would certainly have some velocity in this direction, suggesting that it would have kinetic energy. Now, that energy now is clearly with the block. When the block contacts the spring, then the spring has to do negative work on the block in order for the block to be brought to rest. So if we look at the way the definition has to work, we know the unbalanced force is what causes net work to be done. When the block hits the spring, there's going to be an unbalanced force acting on the block. Hold on. All right, so, yeah, I heard that, bro. So, when the block gets there, the work on the block has got to be, by definition, negative. And I'm not saying that because we derived it that way. I'm saying that because we know the change in kinetic energy has to equal the work done on the block. That's also, a absolute. So the object having no velocity after the contact with the spring, and clearly an initial velocity when it hits the spring, is going to necessitate a negative amount of net work done on the block in order to bring it to rest. So it was a natural consequence that when we derived the work done by the spring, it had to be negative. Now, I need to be careful here because as I describe this to you, I want to make sure I don't become complacent. The spring did work on the block, bringing it to rest. But the block also does work here. The block does positive work on the spring to compress it. I want you to consider, if we talked about what the block does to the spring, the block is going to apply a force in this direction on the spring. And the block can't push any harder on the spring than the spring pushes back on the block. Those two forces would have to be Newton's third law force. The force from the spring on the block would have to equal the force on the block from the spring. So we know the force on the spring from the block would be just kx, not negative kx, but positive kx. This is the force on the spring from the block. We derive that work, it will be positive. So the block does positive work on the spring to compress it, while the spring is doing negative work on the block while being compressed. I know it sounds like we're splitting hairs, we're not. We're carefully making sure we understand the flow of energy here. The block had energy. The block gave the energy to the block spring system that was created the moment the block touched the spring. The most difficult to understand, although we're trying to trace the energy stays with an object until work is done on that object. Something has to do work on the object in order for that energy to be transferred to someplace else. But it's also about force. Force is the connection between the objects that transfers the energy. That's why when we talk about the block touching the spring, the moment that they touch, Newton's third law is the reason there are two forces. Because there's the transfer of energy is taking place because of the two forces. That's why they're equal and opposite. One of them is taking the energy away, and one of them is granting the energy to the other object. And it occurs with that connection. So for all contact forces, it's quite literally because they're touching, they're transferring energy. And the conduit, the connection, is the force. The method is work. So although work is a calculation, it's also really the thing that transfers the energy and allows us to trace it, which means all conservation of energy problems that you've seen in the past can all trace the way the energy flows by looking at the individual amounts of work done. And it all will always come down to Newton's third law. That is the connection. I didn't do this last year in AP1, and I wouldn't do it this year either, because AP1 students don't have the appreciation nor the need to know what's really going on. It's just too much. I started this conversation by reminding you about the concept of potential energy, gravitational potential energy. When we lift the box, work's being done. That part is not a surprise to you. If I lift the box, then we're talking about my force on the box. But I would like you to consider, what is the work done by gravity? Okay. If the box is lifted into the air a distance h, the work done by gravity would have to be F dot delta x. Because the force is constant near the surface of the earth. However, as you're lifting the box, the force of gravity is mg and it's downwards. But the displacement of the box, the delta x, is upwards. So by definition, the work done by gravity would be mg times h times the cosine of 180 degrees. So that the work done by gravity will come out to be negative mgh. Now first, this should tell you why h requires reference, because there's always a starting position. When we defined potential energy last year, we didn't define it based on work done. We defined it differently. But the true definition requires that we consider the work began by moving the object from a starting place. Like I described yesterday, when you lifted the box from the table, the box doesn't get more energy because it's suddenly above the floor. But somewhere, somehow, somebody had already done work to get the box to the table, which is why the reference level is always arbitrary. Now, in this context, the work, again, has to be negative. Because if the box weren't lifted and instead the box started to hit the ground and were thrown upwards with some velocity, then the box would have kinetic energy at the starting point. The work done by gravity would have to be negative in order for that energy to be transferred to the Earth box system. Now, the box is part of that system at the start. Giving it kinetic energy meant it got the energy from something else, me hitting it or throwing it. But its motion every point thereafter is really controlled by the interaction it's having with the Earth, which is why, again, work is negative. So, this is probably the most important definition of the year. One that I really glanced over last year and didn't spend enough time really nailing it down. We will define potential energy. Okay, we're going to define potential energy. And you're not going to like this. The change in an object's potential energy is equal to the negative of work done by a conservative force. We'll define potential energy as the negative of the work done by a conservative force. This is why all of our expressions for potential energy are positive, but all the work done by those forces are negative. We are going to set this by definition. This is not a law. This is not a theory. This is how we define the word potential energy. So potential energy is not like kinetic energy. Kinetic energy can be derived theoretically from first principle laws, which means kinetic energy exists apart from any system. The concept of potential energy is created by humans as a means of tracking energy. I don't know that potential energy actually exists as some quantity. We know it exists because work can be done by these forces. So we as humans have defined this quantity to help us shape and understand the nature of energy. But be aware, the box and the table example is important. The box doesn't suddenly have energy because you move it from being above the table to being above the floor. That's not something that's with the box. Okay, that's different. The box has energy because work was done against a conservative force. You lifted the box against gravity. You pushed the box against the spring. You did the work against the conservative force, and that's why the energy is stored in the system. So this definition is going to come back on us several times in the next couple of weeks. But we define it and set it as our definition, that the change in an object's potential energy is equal to the negative of the work done by a conservative force. Okay, so a long way to get there, but I really want that big and bold and in your notes. because we're going to deal with gravity in a little bit. And gravity's negative. So we're going to find that there's something different about this, something different about our characterization of energy. And it has to do with potential energy specifically. Because it's been set by definition, it can be positive or negative. It's not something that's holistic. Now, I do have a footnote to our discussion. Discussions of energy are often characterized by things that we can see, like roller coasters, pushing against springs, spring launchers, stuff like that is real simple to see. But in the real world, energy transfers are managed by how long they take. And you'll notice the thing about all energy questions is that they are devoid of time. Not once are you going to be able to figure out how long one of these things takes. That's the question that's always left out. Potential energy, let me say it, you guys, how long it takes for the energy to be transferred. That's where the term power comes in. And in prior years, I would teach this kind of as a side piece, but this year I really want to put it front and center. Power, by definition, is the rate at which work is done. It's a derivative. It's the derivative of the work with respect to time. This is going to have big consequences this year, because I'm teaching it different. So I want you to understand that first, it's a derivative, and it can be written two different ways, dw dt or dE dt. I want you to be clear that both of these represent power. One of them represents the rate at which work is done. The other one represents the rate at which energy is consumed. Not all work is conservative, so sometimes energy is just lost to the system. But power is a rate issue. It's how fast something is happening. So you can have any two cars are very likely to be able to get to 50 miles an hour. The more powerful one gets to 50 miles an hour faster. We tend to use the word power to indicate strength, and that's not really what it's about. Power is about speed. Things that are more powerful do things faster. You need to really understand something about this, though. Having a lot of power doesn't mean you have a lot of force. I'm going to say that more than once because you really need it in your notes. A powerful engine, in physics terms, isn't stating that it applies a large force. You can buy a powerful motor, it may not be able to lift a piano. It might be able to lift something light very quickly, but it might not be able to lift anything heavy. So when we talk power, we're not talking force. If you buy a motor, you need to figure out if that motor actually has the lifting force you need. Motors tend to be rated with two things, their power rating, and often they come with a torque rating. The torque rating tells you how hard the motor turns. That will tell you whether it can lift something or not. The power rating is how fast it does work. Now, with that being said, we already have a definition for work. If I take the integral away, work is F dot dx. Now, I'm writing it this way because it comes from knowing that work is the integral of F dot dx. But if I take away the integral sign, I can write this as a derivative. So these two statements, for you guys who are just getting to this point in calculus, are the same. Because you can take the derivative of both sides. When I take the derivative of both sides, that gives me work. So if I strip off the integral, I get the derivative function. So I want you to think about this for a minute because it suggests that the derivative of work with respect to position is force. But the derivative of work with respect to time is power. Both of these derivatives have real use, and we will use them both in this class. First, what this means is that you can determine the force that was used to do work by taking the derivative of work with respect to position. By doing that function, you'll get back force. But you can't confuse this with the rate at which work is done. These are two separate derivatives that generate two different meanings. And so you can't like just throw them around. On the other hand, if you start with this derivative expression for work, you could divide both sides by dt. This will give you a different way of expressing power in terms of force. This is an expression of power as it's consumed by moving an object under a force. So like when we talk about your car, if you want to travel at 50 miles an hour, well, then the amount of power your car has to have will be determined by the force it applies to maintain the speed of 50 miles an hour. This computation of power and this computation of power represent the same thing. We will often talk about power in algebra terms, which will be the change in energy over the change in time. This could be as simple as looking at the change in kinetic energy over time. All these represent different ways of computing power. The units of power is a joule per second, which is affectionately called the watt, after I believe James Watt. I'm not sure if I know his first name. I don't know what he's famous for at all, to be quite honest. What's that? Steam engine? Okay. Cool. I believe that. The horsepower is also a unit of power. I don't know the equivalence between horsepower and watt. It's out there in your book. What is it? I'm sorry, did you have the answer? No, there's an actual physical quantity called the horsepower. It used to be based on the horse about, 300 years ago, 400 years ago, but that's not how you rate it now. So the horsepower in the watt, I want to say it's several thousand watts as a horsepower, but I have no idea what it is. We could probably ask Siri. It'll never come up on our homework or anything like that. But I do want you to understand that the watt is the standard unit of power. We'll use it a lot. More in E&M than in this class. You guys have E&M. We use power all the time. In this class, we don't use it as often. But because all of you are probably going to be homeowners at some time, you buy your electricity in units of energy, but they always sell you energy in units of power. In your home, you buy it in terms of kilowatt hours. This is the standard unit of energy when you buy your electricity. Do you see why that has to be an energy? It's a unit of power multiplied by time. So this is a unit of energy, and it generally is how you buy your electric power in your home. Right now, I think that most of our electric companies are selling the kilowatt hour under $1 a piece. But you're usually burning through them pretty quick. When you buy appliances, look for that symbol, kWhr. That's actually telling you how much energy it takes to run that device. The United States actually requires that all appliances give you the energy consumption of the device at the point of purchase. So if you walk through Lowe's or Home Depot or Sears or any of these stores that sell appliances, there'll be a number out front here. That number is how much energy that unit requires for a year's worth of operation. Federal law requires that all manufacturers of appliances provide that information to you, the homeowner, so that you can make a a judgment about whether you want to use that device or not. Look closely at the fine print on these things. Because believe it or not, it's a big deal when you go to buy stuff like that. And every appliance in your home had this label on it.